Hello everyone, I'm Yuichi Sudo from Hosei University, Japan. Today, I will talk about time-optimal rotary stabilizing redirection in population protocols. This is a joint work with Ryo Daiguchi, Taisuke Izumi, and Toshimitsu Masuzawa. First, let me explain what are population protocols. Population protocols is a computation model which represents a network of possibly mobile devices. Possibly mobile means that each device moves, but it can't control its own movement. Typically, a network consists of a vast number of tiny devices. For example, this model can represent a sensor network to monitor flocal birds, where a sensor device is attached to each bird. The devices have very small wireless transmission power, so they can communicate only when two of them come sufficiently close each other. Recently, this model is also supposed to represent the molecular computing. This model has been extensively studied since Anglin et al. Introduced this model in POJ 2004. In this model, we call a network a population. A population consists of identical and anonymous state machines called agents. At each step, one pair of agents has an interaction. When two agents have an interaction, they send their states to each other and change their states depending on their current states according to the transition function specified by an algorithm. We must assume some kind of schedulers to guarantee the stabilization of an execution and to evaluate the time complexity of an algorithm. We usually assume the uniformly random scheduler. At each step, this scheduler selects one pair of agents uniformly at random from all pairs of the population. Our work focuses on the redirection problem in population protocols. There are two categories of redirection that have been intensively studied in the literature. One is the standard or non-self-stabilizing redirection. In this category, we can assume that in the beginning of an execution, all agents are in a common initial state we specify. Starting from the configuration such that every agent is in the common initial state, we must elect a single leader and keep it thereafter. The other is a self-stabilizing version of redirection. This problem requires that starting from any configuration, we elect a single leader and keep it thereafter. Our work is devoted to the second category, but let me explain briefly the results of the first one in the literature. Under the uniformly random scheduler, the stabilization time of an algorithm is evaluated in expectation or with high probability. In the rest of this talk, let me focus on expected stabilization time. Formally, the expected stabilization time for redirection is the expected time to reach a configuration such that there exists exactly one leader and no agent changes its output after the configuration. In the field of population protocols, we usually express the length of a period by a parallel time. Parallel time is the number of steps over the number of agents. For example, if we require 120 steps to stabilizing expectation for the population consisting of 6 agents, then we said that the expected stabilization time is 20 parallel time. There have been a lot of works devoted to the redirection problem in the population protocols, as you can see in this figure. The horizontal line of this figure shows the expected stabilization time, and the vertical line shows the number of states required by algorithms. Interestingly, in the field of population protocols, we do care logarithmic factors and have tried to improve the complexities little by little. For example, improve the stabilization time from log cubed n to log squared n, and improve the number of states from log squared n to log n, blah blah blah. The last year, one of the stock papers that is depicted in green in this figure gave both time and space optimal algorithm and finished this sequence of improvements for redirection. This algorithm is elegant and amazing. I'd like to say congratulations to the authors of this work. Okay, so let's move on to the second category, self-stabilizing redirection. The self-stabilizing redirection problem requires two properties, convergence and closure. Convergence property requires that starting from any configuration, a population must reach the safe configuration eventually, where exactly one agent is in a leader state. Closure property requires that after a safe configuration is reached, the population must keep the single leader forever. In other words, once the population reaches a safe configuration, no agent can change its output. I am a leader or I'm not a leader. But unfortunately, we have very strong impossibility results for self-stabilizing redirection. There is no self-stabilizing redirection protocol unless every agent knows the population size n exactly. Note that we want self-stabilizing algorithms to attain fault tolerance. However, the knowledge of the exact number of agents inherently results in no tolerance for faults. This is because the algorithm assuming the knowledge of the exact number of agents do not work if just one agent becomes out of order and the number of agents changes. So we cannot design any practical self-stabilizing protocols. So we have a natural question here. Is there any way to design a practical and fault-tolerant redirection protocol? The answer is yes. The notion of root stabilization was introduced by our old paper that was published almost 10 years ago. Root stabilization is a variant of self-stabilization that relaxes the closure property of the original self-stabilization. Roughly speaking, root stabilization allows the population to deviate from the specification even after it reaches a safe configuration. But it must be guaranteed that the deviation occurs only after an extremely long expected time, for example, exponential time. Root stabilization is powerful and useful to design fault-tolerant population protocols. For redirection, the knowledge of the exact number of agents is no longer needed. All you need is the assumption that the agents know a common upper bound on the number of agents. We denote this upper bound by capital N. Here, we assume that this capital N is not extremely larger than the original N. That is, we assume capital N is a polynomial in small n. This table shows a list of loosely stabilizing redirection protocols in the literature. The last one shows tau log cubed n convergence time and n to the power of tau holding time. Here, tau is a design parameter of this protocol. For example, if we set 100 for tau, then the convergence time is log cubed n and the holding time is log to the 100, very large polynomial time. Moreover, we can increase the holding time even longer with increasing tau to a super constant value. Since the holding time is extremely long, these loosely stabilizing protocols are practically equivalent to self-stabilizing algorithms. So we have answered the previous question. Yes, there is a practical and fault-tolerant redirection population protocols. Then the next question is how short convergence time we can achieve as in a sequence of works devoted to the non-self-stabilizing redirection. We have a low bound on the convergence time depending on how long holding time you want. This theorem claims that for any beta greater than 1, if an rudely stabilizing redirection protocol has beta expected holding time, its expected convergence time is big omega of log beta. So if we want an n to the power of tau holding time, every protocol requires at least tau log n convergence time, and the non-shortest convergence time is tau log cubed n. So we have log squared n factor gap. This slide shows the contribution of our work. We have closed the gap for any parameter tau. When you want n to the power of tau holding time, this protocol achieves tau log n convergence time that matches the low bound. Moreover, this protocol also decreases the number of states compared to the previous protocol from tau squared log n to the power of 5 to just tau log n. This is the image of the performances of our algorithm. The proposed algorithm shows optimal convergence time for the holding time of any length you want. Okay, in the rest of this talk, let me explain the proposed protocol. This is an overview of our protocol. Execution of this protocol repeats two phases called check phase and election phase synchronously and forever. We must consider any initial configuration. Thus, in the beginning of execution, the population may be in a mess. That is, some agents are in the check phase and the others are in the election phase. Our protocol recovers synchronization in tau log n time from any such configuration, and once the synchronization is recovered, the execution proceeds like this. All agents are in the check phase, then after sufficiently large tau log n time, some agent enters the election phase, and in a very short time, all agents enter the election phase. After that, all agents keep the election phase for sufficiently large tau log n time. After that, some agent goes back to the check phase, and soon all agents go back to the check phase. Execution repeats this behavior in an extremely long time, that is, n to the power of tau time in expectation. Note that once synchronizer failed, the execution of this protocol recovers synchronization in a tau log n time again. Let me explain what the agents do in the check phase and the election phase, respectively. The goal of the check phase is to detect the absence of a leader. If no leader exists in the population, the agent tries to create at least one leader. Our protocol achieves this goal with high probability. That is, the probability 1 minus big O of 1 over n. The goal of the election phase is to decrease the number of leaders to 1 when 2 or more leaders exist in the population. Our protocol achieves this goal not with high probability, but with a constant probability. Above all, starting from any configuration, the execution first recovers the synchronization. Then, if no leader exists, the population creates at least one leader in the next check phase with high probability. After that, the number of leaders will be decreased to 1 in a constant number of repetitions of election phase in expectation. Thus, our protocol reaches a safe configuration where exactly one leader exists in big O of tau log n time in expectation. After that, the population keeps a single leader until synchronization fails or the absence of a leader is mistakenly detected in the check phase. That is, we encounter a false positive detection of the absence in the check phase. However, these errors occur with very low probability depending on tau at each repetition of these two phases. So the expected holding time is n to the power of tau. This is an overview of our protocol. To design the proposed protocol, we use many existing techniques in the field of population protocols. One of the main difficulties is how to implement a loosely stabilizing synchronizer that recovers synchronization from any configuration and keeps synchronization from extremely long time. To implement a synchronizer, we use a countdown timer called countdown with higher value propagation, abbreviated to CHVP. Recently, the tight analysis on the expected time of countdown by this timer was given, so we can use this countdown timer for our synchronizer. CHVP is useful, but using it alone is not enough to implement the synchronizer. So we introduce a new technique called mode switching that I will explain later. The other difficulty is how to achieve the goal of the election phase. That is, how to decrease the number of leaders to 1 with a tau log n time with a constant probability. Fortunately, we can use the existing tool called quick elimination that is based on the lottery game presented by Aristotle in 2017. In this work, we obtain a new observation that this module, quick elimination, elects 1 leader in because of log n time with a constant probability. Quick elimination uses a well-known technique called epidemic. However, the speed of epidemic is apparently influenced by the newly introduced module mode switching. We also proved that the mode switching does not slow down epidemic asymptotically. We do not need a new technique or new analysis for the check phase. All you need in the check phase is to detect the absence of a leader, and this can be easily implemented by a simple epidemic once you get a synchronizer. In this talk, we will explain only how to implement the synchronizer owing to the time constraint of this talk. First, let me briefly explain CHVP. Each agent has a variable called timer that maintains a non-negative integer. The transaction is very simple. When two agents have an interaction, they compare their timers and take the higher value and decrease it by 1. The resulting value will be assigned for the timers of both agents. If we set a sufficiently large fit of tau log n value for the initial timer value Tmax, then we have the following two properties. One is that starting from any configuration, the population will quickly reach a configuration where all agents have similar values with very high probability. Here, quickly means within big O of tau log n time, and with very high probability means the probability 1 minus big O of n to the power of minus tau. Moreover, those similar values are close to the highest value in the initial configuration. In the example of the above figure, the highest value in the initial configuration is 973. Then the agents will quickly have timer values close to 973 with very high probability. The other property is that starting from any configuration, the timeouts of all agents will quickly become zero with very high probability. Using CHVP, one may think of the following naive synchronizer. Use CHVP with setting the initial value tmax equal theta of tau log n. Then add a timeout rule. When two agents with zero timer value meet, then both of them reset their timeouts to their initial value tmax. And finally, map timer values to the check or election phase like this. That is, if the timer value of an agent is larger than or equal to the half of the initial value, then the agent is in the check phase. Otherwise, the agent is in the election phase. Thanks to the good properties of CHVP, this synchronizer seems to work correctly, but unfortunately, we have one big issue. This synchronizer will cause frequent chattering. Consider that the initial value for CHVP is 100. Once the synchronization is recovered, all agents have similar timer values. So if one agent goes from the check phase to the election phase by decreasing its timer from 50 to 49, then it probably meets an agent with timer values larger than 50 soon. So it goes back to the check phase immediately, and it will decrease timers and goes to the election phase again, but still the population have agents with timer values higher than 50, so it may goes back to the check phase soon again. This chattering behavior is crucially harmful both for check phase and the election phase, so we can't use this naive synchronizer. Next, let's consider a more sophisticated synchronizer. In this synchronizer, each agent maintains a variable named phase that indicates which phase the agent belongs to. Each time an agent encounters a timeout, it resets its timer to the initial value tmax and flips its phase from the check phase to the election phase, or from election phase to the check phase. To specify the rule when two agents with different phases meet, we divide the agents in the check phase to two classes. One is agent with timer values larger than or equal to tmax over 2. The other is agent with timer values less than tmax over 2. When a check phase agent with high value meets an election phase agent, then the election phase agent goes back to the check phase and resets its timer. When a check phase agent with low value meets an election phase agent, then the check phase agent goes to the election phase and resets its timer. One can easily observe that no chattering occurs anymore in the transition period between two phases. However, we will have another issue. This synchronizer requires tau log n states, and the module quick elimination used in the election phase also requires log n states. So the combined algorithm requires tau log squared n states in total. Thus, we need additional technique because our goal is to design a loosely stabilizing leader election protocol with only tau log n states. We decrease the number of states by introducing a new technique called mode switching. Agents in the election phase maintains their modes. There are two modes. One is an elector, and the other is a timekeeper. Electors maintains a variable named level and is devoted to the module quick elimination. Timekeepers are devoted to countdown timers, so countdown timers so that the population can move back to the check phase after a sufficiently large set of tau log n time. Similar kinds of techniques to decrease the number of states are often used in the field of population protocols. A big and important difference is that in the mode switching, the agent dynamically and frequently switches their modes from a lector to a timekeeper and from a timekeeper to a lector. We have two switching rules. When two non-leader lectors with the same level meet, one of them becomes timekeepers. The condition marked red with the same level is needed to guarantee the progress of quick elimination. When two timekeepers meet, the one with higher timer values becomes electors. Here, note that no higher value propagation is done. That is, we adopt simple local timers for the election phase instead of CHVP. But still, we can recover synchronization starting from any configuration thanks to the nice properties of CHVP executed in the check phase. One may think that we can equally divide the population to electors and timekeepers when the population moves from the check phase to the election phase. And so dynamic mode switching is not necessary. But we must consider arbitrary initial configurations, including a configuration where there is no timekeeper, like this figure. Clearly, with the mode switching from electors to timekeepers, we encounter the deadlock. So we require the switching rule from electors to timekeepers. If we adopt only the switching rule from electors to timekeepers, once the population enters the election phase, most of the agents will become timekeepers soon. It severely damages the speed of epidemics so that quick elimination does not complete in tau log n time. From these reasons, we need both the mode switching rules from a lector to a timekeeper and from a timekeeper to an elector. By the mode switching, the whole protocol consisting of the synchronizer and the quick elimination uses only big O of tau log n states in total. So we have achieved the desired performances shown in this table. In this talk, we omit a few important things. What do the agents do in quick elimination? How does quick elimination elect one leader in log n time with a constant probability? Why the mode switching never slows down the speed of epidemic asymptotically? Please read the proceeding if you are interested. Thanks for your time.